Okay, I'm just going to make a quick video for you to review the electron configuration, the light and waves. So I'm just going to run through this. Feel free to stop the video as you want, pause the video as you want, skip questions that you already know. It doesn't matter to me. This is just for your studying purposes. So number one is a wavelength, and that's represented by the symbol lambda, which is a Greek letter. Both 3 and 4 are antinodes. Number 5 is a node. And number 2 is amplitude. And the symbol for wavelength is the lambda. So something that you need to remember for the electromagnetic spectrum is that the visible light is sort of in the middle. And that one's pretty easy to remember. But next to visible light, on the lower energy side is IR, or infrared. Infra means inferior to red, or lower than red. Then we have microwaves, and we have radio waves. And all of these kinds of waves are going through the air all the time. In the room that you're sitting in right now, there's all of these kinds of waves. There's probably not as much ultraviolet or UV. There's probably little or almost no X-rays. They're pretty high energy, and hopefully not hardly any gamma rays. So these have a very short wavelength, a very high frequency, and very, very high energy. And on the other end, radio waves have a long wavelength, sometimes as big as a building. They have a low frequency and they have low energy. So if you can remember that red has low energy, this will help you fill in all the rest of this chart. So what colors of light have more energy than blue? You could say violet. Technically, you could say ultraviolet, X-rays, and gamma rays, even though we can't see those colors. What types of light have longer wavelength than the infrared? That'd be microwave and radio waves. What occurs in order to have an electron emit light? They must lose energy from a higher level to a lower level. So they must fall back down from a higher to a lower energy level. Okay, so on number 11, there's some diagrams like this in your notes, but an electron becoming excited, the zero state is called the ground state, and they can be promoted to one of these other energy levels. We'll just call them 1 or 2. So these are excited states. So an electron becoming excited would go up to one of these states. It can actually go from 1 to 2. And then returning to its ground state, I'm just going to incorporate number 12 in the same drawing. So if it goes back down to its ground state and gives off light, we'll switch colors to red or something. So if it goes back down, it gives off light in photons. Anytime it goes down to another level, it gives off a different color of light. Okay, so I wrote on this earlier today. I'll just erase that. Okay, so energy emitted by light. If you're emitting energy with copper ions, we'll go ahead and use green because that's the answer to the color. So let's say you have a Bunsen burner here, and you put your little Q-tip down in the Bunsen burner. What's happening in that Bunsen burner flame as you put the copper in there? The energy from the flame is going into the copper, and it's causing the electrons to be excited, and then after they fall back down, they give off colors of light, usually green. So that's what's happening. Okay, so the relationship of wavelength and frequency of light. So here's the equation that shows that relationship. There's wavelength, and we have frequency. My dog is sitting in here chewing on her bone, so if you hear something in the background, that's it. So in order for this to remain constant, we have to have the speed of light stays the same. So as the wavelength increases, the frequency decreases, and vice versa. So it's an inverse relationship. So what is the equation to calculate wavelength given frequency? That's right here. What is the equation to calculate frequency given the wavelength? You can kind of rearrange these if you want. So I think what I was going for here is if you have wavelength, that's going to be speed of light divided by frequency. If you have, if you're given the wavelength and you want to find frequency, it'd be speed of light divided by the wavelength. Just algebra. Okay, so calculate the wavelength of a photon of light that has a frequency of 6.21 times 10 to the 14th hertz. So we know wavelength, we know frequency. So you have to use an equation that has those two things. So here's our equation. And we have 3 times 10 to the 8th meters per second. Your wavelength, we don't know. And your frequency gives it in the problem. Okay, this is where a scientific or graphing calculator comes in really handy. Neither of which I have around me right now, so that's a little bit of a challenge. But you're going to divide both sides by 6.21 times 10 to the 14th hertz. So when you put this in your calculator, you either need to put parentheses around each of these numbers in order to get this to turn out correctly, or you need to put it in your calculator with the E button that I told you about. Okay, so I'm going to pull up a calculator really quick. Okay, so I got a wavelength of 4.83 times 10 to the minus 7. If you calculate this and you get something different, if you just want to send me a message on Remind tonight, I'll double check my math. I've been doing my math in Google, which is probably not the best. So, okay, so calculate the frequency if you have a wavelength of 5.27 or 5.25 times 10 to the minus 7. So again, we're going to use the same equation here. We know the speed of light. Speed of light never changes. It doesn't matter if it's radio waves or gamma rays. It makes no difference. Okay, and then we're going to have a wavelength. Millie, no. All right, calculate the frequency. Okay, so we need to divide both sides by 5.25 times 10 to the minus 7. I'm going to put this in Google and get you an answer here, but go ahead and put this in your calculator too, because you need to know how to do it on your own. All right, I got 5.71 times 10 to the 14th hertz. Oh, and the last problem should be in meters. Make sure that you are including the units. Hey. No. Okay. The relationship between frequency of light and energy, that is the energy equation with Planck's constant. So, whoops. All right, so this is a constant, H.